Hello everyone, my name is Cole Schrader and I'm here today to present my work in creating a power hardware in the loop emulation of electrochemical energy storage systems with operating voltages as high as 1 kVDC. So to begin, there is a knowledge gap and confidence gap in understanding the trust of battery management systems. And to kind of go into what a battery management system does is these are the systems that go ahead and actually, for lack of a better term, manage your battery. So they will go ahead and, for example, keep the cells in the balance or the same state of charge. They'll go ahead and make sure that you're not drawing too much current. They'll make sure your cells aren't at high temps where they might start to break down. And so the whole idea of a battery management system is that it monitors the safety of your battery. Currently, there's a big knowledge gap on how these perform on high voltage test beds, and there's really no standard to test them against. And testing them on the device can be costly. Today I'll go through the methodology in creating a test bed and the work I've done so far, as well as explain some of the concepts that are being applied here to safely test battery management systems with this test bed. So to begin, BMSs and battery configuration. For those of you who are not familiar, batteries are configured in typically with a bunch of smaller cells in N series and M parallel configuration, and then that will form a module. And then those modules will be connected in an X series and Y parallel configuration, and this will increase the voltage and current capacity. And these modules will interface with its own BMS card. And so you can get batteries that at the cells are only 3.3 volts, but if you put enough of them, about 270 in series, you'll get an end result of about 1,000 volts. So to kind of go through a typical BMS topology, like I mentioned earlier, the main purpose of the BMS is to keep cells in the same state of charge. The reason why this is important is battery is only as strong as its weakest cell. So if you had one cell at 20% and another cell at 50% capacity, well, the capacity of your battery is going to be actually limited by that one at 20%. So the idea is you want to get them to the same state of charge. And there's two ways to do this. The first way is a passive BMS. What a passive BMS does is it actually dissipates the excess energy in cells as heat, typically across a resistor. So in an example I gave earlier, if you had the 50% and 20% cells, a passive BMS will actually dissipate all the excess power, so both cells are at 20%, but now you can charge them together and now your battery is in balance. For an active BMS, it's a little more efficient as it is able to actually shuttle the charge between them. And so what will happen is they'll both equalize at the halfway point, assuming ideal conditions. However, for this work, we are focusing on passive BMSs as they seem to be more widely available on the 1 kilovolt scale. So to begin, I kind of covered BMS operation. Here we have a K2 BMS, and we actually created a LabVIEW plugin that goes ahead and monitors cells on the battery. This is a BMS we actually have currently deployed on a 1,000-volt battery. And in our case, the reason why all of this is important is because these BMSs will frequently integrate with external controllers, things like load shed and ramp rate. And so we are relying heavily on the fact that these BMSs also report correct cell voltages, monitor the battery current, as well as the SOC and energy so that we can estimate how much battery power we got left. And we also want to prevent scenarios such as cell under voltage and cell over voltage, which would damage the cells permanently, and prevent overcurrent, which might damage the cells as well, or cause a situation where thermal runaway is of importance. So it's critical that we have a way to test this BMS before we actually implement it on the 1,000-volt battery so we can guarantee that it will operate in the condition we expect it to. So how would we begin to integrate a BMS into a power system controller? So to begin, like I showed on the last slide, we had that LabVIEW plugin that monitored voltages, and so this is how we do it. So each one of those modules, just like when I showed the BMS earlier, will interface with a secondary card. So each of those secondary cards can monitor 10 cells. And what you do is you get enough of those secondary cards so you can reach the top of your battery, and all of those connect to a primary where all that data is collected, and it can be interfaced with a power system controller. And then, of course, you would want the output of your battery to be hooked up to a supplier load that the power system controller would communicate to charge or load the battery on. So, how would a BMS operate? So I talked about how it would balance the cells. How does it quite do that? So the very first kind of predictive way in how a lot of BMSs operate is they'll actually have manually set thresholds. So on those balance cards I showed earlier, what will actually happen is you'll have a balance threshold as denoted by the dotted black line, and this is the point at which the BMS would close its contact and dissipate excess power on the cell. And then what you'll do is you'll have these red lines where the BMS will open up or even request a charge or load to go ahead and dissipate that power or get power into the battery. And those are denoted by the two dotted red lines. And so what will happen is a BMS will open up, if you look on the top graph, it will open up right here on this dotted red line, and it will go ahead and dissipate it until it reaches the balance threshold, and then you can go ahead and recharge it again and continue this process until the cells are in balance at that balance threshold line. Now what's going to be of interest to us is we are going to do something called a hardware-in-the-loop simulation. So we're going to actually deploy a model of a battery onto our system, and what this will allow us to do is we could actually test faster because we don't need to discharge the battery or force an uneven discharge. We can actually go ahead and set the SOC manually in real time, and then that will decrease our test time as well as allow us to test certain scenarios in more isolated conditions. And so this is an ability that I will go into talking about, as it is a very neat feature of using a hardware-in-the-loop simulation. So I mentioned hardware-in-the-loop. What is it? Hardware-in-the-loop simulation allows for us to actually deploy a model that is in software to the external world. And why that's important is now a device might look at this output and think it's a real device. And so the simple way of saying this here is what we're going to do is we're going to take that model of a battery and we're going to hook it up to a power supply. And as far as the battery management system is concerned, it sees an actual battery. And so that allows us to, in a way, almost fake the BMS into thinking it's hooked up to a battery. And that will allow us to actually have a situation that A, is much faster to test, B, much safer because the hardware-in-the-loop simulation can be turned off and there isn't any chance of thermal runaway, and it's a power supply, so its output is much more limited. It also allows for the monitoring of all the inputs and outputs, such as the current voltage from an external source. So there's a lot of advantages to using this HIL simulation. Lastly, it also would let you change things quickly in your model. So if you wanted to change cell chemistry or even just small parameters such as the internal resistance of a chemistry to fake a state of health, you could do so relatively easily without changing your system significantly in any way. So for the testbed, 3 options were considered for our use case. The first is to test directly on the battery. This is not a great choice, as the very first thing is that you carry all the safety risks I've been talking about testing directly on a battery, such as thermal runaway, chance of fire, leaking cells. But the 2 other points that weren't really mentioned but are factors as well is you have the longer preparation time to adjust the battery SOC. So on that graph of BMS behavior, I showed how we could instantly change the SOC with hardware-in-the-loop. You can't do that for a real battery. You'd have to go back there and manually dissipate or recharge cells to put it out of balance, and then conduct your test. And then the last point of or problem with testing on a real battery is it's the only battery that can be studied. If you create a 1,000-volt lithium-ion battery, that's the one you're studying. To study another chemistry, you'd have to rebuild the entire battery with that chemistry. At that point, you're basically rebuilding the testbed every time you want to test a different chemistry or a different state. So the second option is using that hardware-in-the-loop I was talking about earlier and multiple linear galvanically isolated power supplies. The primary issue of doing this is these power supplies are typically driven by an analog output or input to the power supply. But that means that if you had a bunch of these power supplies, say 270 for the 1,000-volt battery, you would have to have a very high quantity of those on your hardware-in-the-loop system. One to dictate the voltage, but then one to measure the voltage and current on the output of the power supply. So this results in a system that would require easily 270 times 3 analog connections. And so it becomes very difficult to wire, as well as find a system that has that many inputs and outputs, as well as a power supply, linear galvanic isolated power supply with a 1,000-volt isolation. So our last option is the commercial battery emulators. There are companies that actually do design battery emulators, and many of them do come with a high isolation voltage, either at or exceeding 1,000 volts. Communication with those is handled via Ethernet protocol or PXI connections, thus the large amount of analog inputs and outputs would not be necessary. And individual units typically contain multiple battery cells and outputs, and so you wouldn't need 270 units. You would need just a fraction of those. So commercial emulators seem to provide us with the most flexibility, so we looked at options from Chroma, Hioki, and SpeedGo. So to begin, let's talk about the Chroma. So the Chroma battery emulator has 16 channels, meaning that it could emulate 16 cells per unit. Its voltage range is 0 to 5 volts, and people might note that that voltage is not very high, but for a cell, you only need to really go up to 3.3 volts or so, so this is perfect for our purposes. And then it also has a 5 amp rating and 2000 volt DC galvanic isolation. So we have procured one of these units for our purposes, and we actually do have some tests in this presentation using the Chroma unit presented here. The next option we looked at is Hioki. Hioki is very similar to the Chroma, with a very similar voltage rating, up to 5.1 volts. However, it only has 12 channels per unit, and its current is much lower. It's not capable of 5 amps, it's only capable of 210 milliamps continuously. It has the 1000 volt isolation, however, and a latency at 50 milliseconds. So it's a little slower, and it has less current capability and less cells per unit. An option that was of interest to us is the SpeedGo IO991 modules. The reason why they are of interest to us is SpeedGo is actually a subsidiary of MathWorks. And so our models are typically designed in MATLAB and Simulink. So having a company that had this integration with that simplified a lot of the problems that we kind of saw on this testbed. And so they had a product that is capable of 0 to 7 volts, can sync 100 milliamps and source 300 milliamps, but it was only limited to 750 volt galvanic isolation, so it falls short of our target. The one thing of interest too is that its communication method was different. So instead of communicating via the Ethernet cable or TCP communication, like the Hioki and Chroma, this actually communicated to the target computer it was running on via PXI chassis that would then hook up via PXI connection. So this was very interesting in how it was different, as well as the seamless integration into Simulink. Now, SpeedGo did report to us that they were coming out with a new prototype emulator, and it's we are actually going to receive those very shortly. We have a couple prototypes on hand that we have done tests with. However, our full cabinet is going to be arriving this quarter. So this chassis actually has 5 volt and 5 amp capability, just like the Chroma. It contains 12 cells like the Hioki, and it does have a galvanic isolation of 1000 volt DC. And the reason why we went with this option, it was much more financially feasible for us to do so, as it was a prototype for SpeedGo at the time. So, now that we've talked about the hardware, let's talk about the battery model. We are using a multi-physics model developed in Simulink. The model is actually distro D, so I cannot share it with you here. However, I can show you a generic battery model that we have developed in Simulink, as well as the option Simulink has, where they actually have many cells in chemistries already available, and which use a lookup table. Now, to the right on top is an example of that simple model where I went ahead and made modules, and I have a table for the temperature measurement and a load profile to drive these cells. And below are graphs of those at a 1C discharge. What that means is I draw a continuous amount of current from the cells, and the reason why I did this here is to show you how the cells discharge. So some of you may know this, but for those who don't, battery cells do not dissipate in a straight line. So 50% capacity does not mean you're at 50% voltage. You'll notice that it has like this plateau effect, and at the start you can see a small ramp, vertical ramp, and then at the bottom you can see that it starts to go down significantly faster than in the middle. And why that can be of significance is you'll notice that all these cells, they start at 93 plus or minus 2%. So at the top end, you might not see that your cells are out of balance, except for at the tiny little ramp at the start, and near the end, when all the cells are almost dissipated, you'll see that it has a huge effect, 2 or 3%, on the voltage that the cell is at. So that's just for anyone who is unaware, and the importance of the BMS, as you can see, a small percentage point of SOC will actually have exponential effects at the end of your discharge. So here are some of our preliminary tests. When we had the Speedgoat IO991, we had 3 of those to test with, starting off while Speedgoat worked on the prototype. And to the top right is the tool we use to change the SOC. So I can actually, in this tool here, select the module, and then on the module I have sliders for each cell. And I can set the SOC instantaneously and monitor the SOC of the cells in real time as our model runs in Simulink real time. The main limitation of the Speedgoat IO991 that I did not mention previously is it did not have current sense built into them. So our lab developed a little current sense board in which we could plug these cards into, and this would measure the current and then feed it back into via an analog input card on our Speedgoat target machine, the currents, and so thus we could we integrated the current measurement feedback to update the model. And then this middle picture is actually the Actia BMS balancing, and I'll discuss those results in the next slide. So here is the Actia BMS. You'll see that the cells are out of balance, and that is denoted by cell 4 and cell 5 being above 3.5 volts. And the Actia BMS behaves a little differently than the predicted BMS results given previously. Before, the balance threshold was set, typically by a user or programmed into it. On the Actia BMS, what it actually does is it goes ahead and balances the cells down to the lowest cell. So the balance point is dynamically set to the lowest cell voltage. And so it will continue to balance cells 4 and 5 until it reaches this gap here. And on this BMS, we are running 10 cells. I just plotted 5 because it would be much simpler to view. And so we can notice that this BMS and how it behaves and how it was different than our predicted results. And so this kind of highlights part of the importance of testing these systems. Another example of this, and to prove our ability to rapidly change the SOC, is a similar test. However, the cells start off in balance at this bottom graph here, and then I bring it out of balance at about half times 10 to the 5th seconds. And you can see the BMS starts balancing all the cells I brought up. And you'll see just right here there is a little hysteresis on every once in a while. It thinks the orange is a little above, so it does turn on that balance. And we think that is a consequence of the dynamic balancing threshold, is it might continuously dissipate a cell or two if it measures the voltage incorrectly. And so this could result in a BMS that balances a cell when you're actually pretty close to balance. And so this once again kind of shows the importance of conducting these tests as well as battery maintenance on it. Now here's to the right, just to get a better view of the currents, because once it's close to balance, you can see some behavior where it almost looks noisy. I put a low pass filter on it. You can see the current goes from the passive draw just from the cells and measuring is less than 10 milliamps. But then once the cell is balancing, you're drawing about between 40 and 50 milliamps. So another BMS we tested, and I showed it earlier on that LabVIEW tool, was a K2. So K2 actually behaves exactly like our predicted results. And so you can see on here we have recharge the cells each time on these vertical peaks. And this recharge I actually conducted in software. So anytime the cells stopped balancing or reached the point where all of them were below a threshold, I would engage the software recharge and then open it up once it exceeded 3.8 volts. And what you'll notice is such as on the cell 4 here in purple, is it will start to merge with the triangle. So here we got the purple coming up, and then you have the red, and then you have the yellow come up, until the end where all the cells kind of form this triangle, and the BMS is now in balance, so you can stop recharging all the cells. And so this top graph is the values I was commanding in my model. So this is what we were theoretically outputting, and this was tested with the chroma cell emulator, not the IO991. So that's something to note here. It was a slightly different test since the current sense was built in and is with the different unit. Now this bottom one, the K2 BMS reports cell voltages, and so we can compare what the K2 BMS measured to what we were outputting onto our chroma emulator, and you can see it follows the same pattern and it's within tolerance for what we wish to see. So one of the problems we did occur or that did occur was on the K2 BMS, we noticed that there was a situation where the cells actually dropped off exponentially. We have not been able to replicate this test. We have seen this occur on our battery, and it did it on our emulator here. We're not sure at this time what causes it, but this once again highlights the whole issue of battery safety when you're testing on BMSs, as this in a real application could cause serious damage to your battery, but also leave you in a situation where you thought you had a bunch of energy left over in your energy storage, and really a bunch of the cells were killed, and so you can't use your battery until those cells are either replaced or individually recharged. And so this is just once again shows the importance of creating this, and so we can find these issues and maybe even figure out a solution and how to replicate them in an efficient and safe manner. So currently, I mentioned earlier, we are kind of limited in testing and have a couple prototype units, but the SpeedGoat final product is coming. So down here on the bottom right, we currently have 5 in this cabinet. We actually have one more unit in cabinet next to it, as each cabinet will be a 500 volt battery that we will tie in series. And so we could emulate up to 72 cells right now. Their final product is coming this quarter, so we will be able to actually finish constructing the 1000 volt test bed. But you can see from preliminary results, I hope, that we already have a pretty good idea of how these BMSs may or may not behave. And so it will be good to test them on the 1000 volt system and see what changes. So, conclusion, I hope I showed you some of the results we got so far, and I've highlighted the importance of testing these battery management systems. Our future results will actually be deploying these BMSs on more shipboard controls. We are currently working with Clarkson University on load shed and ramp rate controls. And we just want to go ahead and make sure all these BMSs for these controls being tested are vetted and safe to use on 1000 volt systems such as this. And so using that emulator test bed to go ahead and test these systems and different battery chemistry only makes sense. I would like to thank General Technical Services as well as the Naval Surface Warfare Center in Philadelphia for their support in this project. And if anyone has any questions, feel free to ask. Thank you for your time.